Hi, my name is Taviso Mukwena, and today I'll be looking at linear programming and basic maximization. So basically, I just drew a mind map to explain what basic maximization is. Now, if you look at the map below, you'll see that basic maximization, or in this term, linear programming, will give you a word problem. Word problem being a scenario where you have certain groups of data and you have to convert that into an equation. Equation being a system of inequalities. So by that, you would be trying to get the maximum profit, or rather the best profit out of that system of inequalities. Now, based on the word problem, you would get how many units per period gives you a particular result, or whatever outcome you're looking for. And that would be, so to define the maximization in our system of inequalities, it would be defined by a less than or equals to sign to say that we're trying to maximize. So you would either calculate or graph the data in order to show that particular result. But let's look at an example to further explain. Cool. Okay, so consider a small business enterprise which makes dresses and trousers. To make dresses, half hour is required for cutting and 20 minutes is required for stitching. And to make trousers, you require 15 minutes for cutting and you require half an hour again for stitching. So the profit on the dresses is 40 rands, and on a pair of trousers is 50 rands. Now, the business operates for a maximum of 8 hours per day. Now the question would be, determine how many dresses and trousers should be made to maximize profit and what the maximum profit is. Now that one is basically straightforward. It tells you that it wants maximum profit. Okay, so I've drawn up a table to break down the problem that we've been given. Now, we've been given two groups, which is dresses and trousers. Those can be considered as X and Y, or A and B, or whatever you want to call them. We've been given two methods, which is cutting and stitching. We've been given profit per unit, which is 40 rands for dresses and 50 rands for trousers. And we've been given the maximum number of hours. So we have a maximum number of hours which we need to work. So I think that should be enough for us to set up our system of inequalities, as we've said. Therefore, if you consider that dresses and trousers are X and Y, for example, that means to set up our system of inequalities, we can add both to give us X plus Y. Now consider the values of X and Y, or rather the table. They've given us, for cutting, half for dresses and quarter for trousers. So now consider those values in the table as coefficients of X and Y. Therefore, in this case, you would have 1 over 2x plus 1 over 4 plus, in terms of hours, they've given us a maximum number of hours to work. Therefore, you know that this is less than or would be equals to 8 hours of work. Same thing for stitching. We can consider it as 1 over 3x plus 1 over 2y at the maximum hours of work of 8. So you can consider your dresses and trousers or your categories as whatever you want to call them. But in this case, for the sake of math rules, you can either call it x1, x2, or x and y. Okay, cool. So now consider the profit we've been given. That can also be broken down into the category where 40 being a coefficient of x can be added to 50 being the coefficient of y, and that will allow us to get the profit. So in terms of linear programming, here this can be considered as the objective function. Okay, so now that we've established a system of inequalities, now we can figure out how we get the maximum profit. Now consider that, oh, there's one other thing I forgot to mention. You need to always state what your x and y values are in accordance to 0. So in this case, x and y are greater than or equals to 0. But our equations, due to maximization, or us trying to maximize profit, are less than or equals to the maximum number of hours, which is 8. So that will help us later on in finding the feasible region, etc. Now we know that the values are whole numbers, which, yeah, so now we need to state that as well. Now, just to know what parameters we're working on. So I've gone through the liberty of calculating what values we need to plot on our graph. So when we graph this and we get our system of inequalities, we need to substitute based on what value we want. So if we want the x coordinate, we need to make y 0, and if we want the y coordinate, we need to make x 0, and yeah, vice versa. So in this case, I think if you look at this, all I did was break down the fraction in order to get that value, and then the same thing applies there, where I passed around the values in order to further break down the fraction. And I got to that answer, which is 2x plus y is equals to 32, and I got to that answer as well, which is 2x plus 3y is equals to 48, right? So now basically we need to create a line in the graph that represents both those system of inequalities with those equations. Rather, in this case, equations, because it's no longer greater than or equals to in terms of graph. So like I said before, I just substituted to get my x coordinate with 0. I substituted y with 0, and then to get my y coordinate, I substituted x with 0. Therefore, for this one, which would be that line where if x is equals to 0, you times that 2 by 0, you'll get y is equals to 34, or 32, sorry. And if y is equals to 0, you get a value of 16. So x is equals to 16. So you get that coordinate there where 0, x is equals to 0 and y is equals to 16. So same thing applies for that other side where you substitute 2x, or rather x by 0 to give you the y coordinate. It will give you 3x equals 48. You substitute that, etc., etc. That will give you a line coordinates as I've ticked there. So now remember, once you've plotted your graph, you need to find the feasible region so you know what values to work with to establish your maximum profit. So now that I know in the back of my mind that we are working with values that are greater than or equals to 0. We know now that the graph should be moving like that due to it being greater than or equals to. So it's moving, its value is greater or moving away from 0. So now we know that these equations are less than or equals to the maximum value or maximum hours worked. So we know that we are working at this point here as if we're moving towards 0. Therefore, that's why I highlighted this area here as my feasible region. So now the points, the vertices, or rather the points where the graph meets, or where either more than one line hit each other within the feasible region, are considered our vertices. So now you need to basically take the points of the vertices and substitute them to the objective function. As you can see there, that's what I've done. In this case, I chose to work with the highest values, or the highest values in regards to the vertices, which is 12 and 8, where the graph meets here. 12 being my x-coordinate, 8 being my y-coordinate. So because that's the highest value, we can safely assume, or if we calculate it, we can see we're going to get 880. But I further did calculations on the other points as well, where the graph meets 0 and 16, I got a value of 800. Where the graph meets 16 is at 16 and 0, I got a value of 640. And where the graph meets, or where the 2 points meet here, at 0 and 0, I got a value of 0. So we can safely say that our maximum profit in this case is 880. So to sum it all up, maximum profit is basically data gathered according to problem solving. So like you saw, we looked at a problem and then we gathered data within that particular problem, and we took that data, we represented it according to a graph, and we gave projections. So projections as to what the possible values would be according to the equation. And at the end of the day, we got to outcomes and goals, or we obtained outcomes and goals in order to basically establish what our projections, or how we would be able to achieve our projections, and in order to get maximum profit. And that's basically it. I mean, it doesn't get more practical than that, aside from the fact that it's just a projection, but I think that sums it all up. Cool, thank you, bye.